So if you take a standard measuring cup, right, and you just scoop up some flour,
Mm-hmm.
and then you take an identical cup and scoop up some granulated sugar,
Right.
they look like they take up the exact same amount of space.
Right.
Like, visually, they are identical.
Yeah, they do.
You'd think they hold the same weight or, the same general presence in a recipe. But if you rely on that visual illusion when you're baking, that assumption won't just ruin dessert.
No, it won't.
I mean, the source material we are looking at today suggests it could literally cause your food to catch fire in the oven.
It absolutely could, yeah.
Welcome to this customized deep dive into Unit 3 measurements and methods. Our mission today is to break down the highly rigid, totally unforgiving physics and chemistry of baking. Because, unlike throwing together a soup where you can just sort of season to taste.
Right, a little this, a little that.
Exactly. Baking is this high-stakes science where the exact mass of an ingredient and the kinetic energy you use to mix it basically dictates everything.
It does. The notes we are analyzing today, they really strip away all that romance of the kitchen.
Yeah.
And they replace it with, well, laboratory conditions.
Totally.
The text organizes the science into two highly dependent pillars. You have measurements, which is about calculating the precise chemical mass of your materials.
Okay.
And then methods, which is about the specific physical forces you apply to them. You really cannot master one without the other.
Okay, let's unpack this, because before the notes even get into the how of measuring, they hit us with a rather brutal look at the why.
Yes.
The text outlines this terrifying domino effect of inaccuracy. Let's look at what happens when you mess up the absolute foundation, which is flour.
Right.
The notes state that if you add too much flour, you guarantee a dry product. And if you add too little, you get a flat product. It sounds simple on the surface, but what is mechanically happening inside the oven there?
Well, you have to look at flour as the active structural framing of your bake. It contains complex carbohydrates and proteins, right? And they are basically just waiting to absorb liquid.
So they're thirsty.
Exactly. When you introduce too much flour into a batter, you are completely overwhelming the hydration ratio.
Oh, wow.
Those excess starch molecules, they act like a sponge. They aggressively pull in every drop of available moisture. I mean, the eggs, the milk, the butter, all of it.
So there's nothing left over.
Right. By the time it bakes, there is no free moisture left to create steam or tenderize the crumb. You are just left with a rigid, desiccated block.
So it's basically a moisture vacuum.
Yes.
And then on the flip side, using too little flour causes a flat product. I'm assuming that means the structural framing just wasn't strong enough to, hold up the roof.
It goes a bit deeper than just lacking strength, actually.
Oh, really?
Yeah. Baking relies on expanding gases, so steam from water or carbon dioxide from your leaveners, and they push the batter upward.
Right.
Flour creates this flexible web that traps those gases, kind of like a balloon holding air.
Oh, I see.
If you don't have enough flour in the mix, that web is way too thin. It's fragile.
Right, because there's just not enough material there.
Exactly. So the gases expand in the heat of the oven, they push against the weak web, and they just shatter it.
Oh, man.
The gas escapes, and the entire structure collapses in on itself.
That makes perfect sense. Now, let us pivot to sugar, because this is where the text completely changed how I view an ingredient.
Oh, it's fascinating.
I always thought sugar was just there for flavor. You add more to make it sweeter.
Right, most people do.
But the source notes explicitly state that too much sugar actually causes burning, and too little sugar results in a pale and tasteless product. I mean, I never connected sugar to the physical color or the burn rate of a cake.
Well, what's fascinating here is that sugar is a highly volatile chemical actor under heat.
Okay.
What the text is referring to here is how sugar dictates the Maillard reaction and caramelization.
Right.
Sugar molecules, they hold onto water very tightly. When you put too much sugar in a batter, it actively competes with the flour for moisture.
Oh, so they're fighting over the wet ingredients.
Exactly. And that competition actually lowers the temperature at which the batter sets.
Wait, so what does that mean for the baking time?
It means because the inside takes longer to cook and stabilize, the outside of the cake is exposed to high heat for way too long.
Oh, I see where this is going.
Yeah, the massive concentration of sugar on the crust rapidly caramelizes, and then it carbonizes.
It literally turns to charcoal.
Yes, turning to charcoal before the inside is even finished baking.
Okay, I think I need an analogy to lock this in.
Go for it.
If I'm thinking about building a structure, let's say flour is the structural framing of a house, right? The wood.
Okay.
And the sugar is like the electrical wiring.
I like that.
If you put in way too much wood, the house is just stiff and dry and kind of unlivable.
Right.
But if you mess up the wiring, the sugar, you overload it, the whole thing literally burns down.
That captures the structural dynamic really well. The
Mhm.
ratio dictates the integrity of the whole material.
Right. And if we stick with that, if you leave the wiring out completely, if you use too little sugar, the house doesn't burn, but it's just cold and dark and pale and boring.
Exactly. That is the exact hazard the notes are warning against. You are balancing the structural matrix of the flour against the tenderizing and browning properties of the sugar.
Wow.
A miscalculation in either direction guarantees failure.
Which brings us back to that illusion I mentioned at the start of Deep Dive. The visual deception of volume.
Yes.
To prevent these chemical disasters, the source material forces us to abandon volume measurements, like cups, and move into exact metric weights.
It's the only way to be precise.
Right, and the text highlights this with a stark comparison. It says, 1 cup of flour equals 120 grams, but 1 cup of sugar equals 200 grams.
The mass discrepancy there is absolutely critical.
It's huge.
You have two ingredients occupying the exact same physical volume, a standard cup.
Yeah.
But the sugar brings nearly double the weight to the equation.
How is the physical difference that extreme? I mean, why is sugar so much heavier than flour when they look like they take up the same space on the counter?
You have to consider the microscopic geometry of the ingredients.
Okay.
Flour particles are jagged, they're irregular and kind of feathery.
Right.
When they pile up in a measuring cup, they don't sit flush against one another. They create these microscopic bridges, trapping massive amounts of ambient air right there in the cup.
Oh, so it's like measuring a cup full of loose leaves.
Exactly. You are measuring a lot of empty space.
Wow.
Sugar, however, is a crystalline structure.
Okay.
The granules are dense, they're smooth, and they're highly geometric. They pack together tightly, displacing the air.
Like a cup full of gravel.
Yes. So when you scoop a cup of sugar, you are getting concentrated mass.
So if a recipe calls for equal parts flour and sugar by weight, and I just blindly use 1 cup of each, I'm actually dumping way too much sugar into the bowl.
Yes, because you didn't account for the density.
And based on what we just talked about, that excess sugar lowers the setting temperature, rapidly accelerates caramelization, and I end up burning the outside of my cake while the inside is just raw batter.
The chemistry is entirely unforgiving of visual estimates.
Clearly.
This is why professional baking operates almost exclusively in grams. But the notes also carry this strict precision down to the micromeasurements.
Right, the liquids and powders.
Exactly, detailing the volume conversions for highly potent ingredients. The text notes that 1 tablespoon equals 15 milliliters,
Okay.
while 1 teaspoon equals 5 milliliters.
Okay, so 15 milliliters for a tablespoon, 5 for a teaspoon. I mean, the math itself is straightforward. A tablespoon is exactly 3 times larger.
Right.
But when I apply that math to the actual baking process, it's a little unsettling.
How so?
Well, if I casually grab a tablespoon out of the drawer instead of a teaspoon when I'm measuring, say, baking soda, I haven't just added a little extra. I've scaled up the chemical payload by 300%.
Which triggers a complete systemic collapse of your batter.
Seriously?
Oh, absolutely. Baking soda, which is sodium bicarbonate, is an alkaline compound.
Okay.
It relies on a very precise pH balance with the acidic ingredients in your bowl to create lift.
So it needs to react with the acid.
Right. If you accidentally triple that volume from 5 milliliters to 15 milliliters, you immediately exhaust all the acid in the recipe.
Oh, no.
Yeah, the leftover unreacted baking soda just remains in the dough, which drastically raises the overall pH level.
What does a high pH level actually do to the cookie when it bakes?
It creates a process akin to saponification.
Wait, like soap making?
Yes, the baked good will taste distinctly like soap or tin.
Gross.
Furthermore, alkaline environments accelerate the Maillard reaction we discussed earlier.
Right.
So an accidental tablespoon instead of a teaspoon will yield a metallic-tasting, heavily browned, rapidly overexpanded product that immediately deflates.
Wow. All because you reached for the slightly larger spoon in the drawer.
Exactly.
It is wild how an innocent mistake in volume scales into a complete chemical disaster.
It really is.
Now, moving past the raw numbers, the text organizes these exactingly measured ingredients into 4 distinct classes.
Right.
We have our dry ingredients, which includes flour, sugar, salt, and cocoa. We have wet ingredients, which are milk, eggs, and melted butter.
Mm-hmm.
Then we have fats, listing butter, margarine, and oil. And finally, leaveners, which are baking powder, baking soda, and yeast.
The source material is categorizing these components strictly by their functional behavior within the batter.
Okay, let's unpack this. Because looking closely at that list, there's a massive paradox hiding right in plain sight.
Oh.
Under the fats category, the text lists butter. But under the wet ingredients category, the text explicitly lists melted butter.
Ah, yes.
Why does heating up a stick of butter completely change its chemical classification? I mean, it's the exact same substance.
Well, the substance hasn't changed, but its state of matter has, and that fundamentally alters its job in the mixing bowl.
Oh, so?
When butter is solid, which is why it sits in the fats category, it has plasticity. It is malleable. In a solid state, butter can be manipulated to trap and hold air bubbles, and it can physically coat flour proteins to block water absorption.
What?
So it acts as a physical barrier and an aerator.
But the second you melt it.
The plasticity is totally gone. Melted butter cannot trap air. It cannot effectively coat flour in the same localized way. It has become a fluid.
Oh, that makes sense.
Its function in the bowl is now to provide hydration, carry flavor, and distribute heat, which is the exact same functional role that milk or liquid eggs play.
Wow.
Therefore, the moment the butter turns liquid, it functionally crosses the boundary and becomes a wet ingredient.
So if I'm looking at a recipe that calls for cold cubed butter, right?
Uh-huh.
And I decide to microwave it because, it's faster to mix.
A common mistake.
I haven't just saved time. I have literally swapped a structural fat for a wet ingredient. I've completely altered the hydration dynamic.
You destroy the intended architecture of the bake before it even reached the oven.
That is wild.
The ingredients are categorized by what they actively do at their current temperature, not what it says on their packaging.
Which provides the perfect transition into the second major pillar of our source notes today. Unit 4, Mixing Methods Theory.
Yes.
Because we now know that temperature dictates function, and exact mass prevents collapse. But having 120 grams of perfectly measured flour and 200 grams of sugar sitting in a bowl means absolutely nothing if we don't know how to physically combine them.
Exactly. This is where the chemistry relies heavily on physics.
Right.
The text shifts focus entirely to the kinetic energy you apply. The physical manipulation of the ingredients, how you push, pull, or beat them, that is what ultimately determines the final texture.
That's all about the movement.
Yes, you can take the exact same perfectly measured ingredients, subject them to two completely different mixing methods, and pull two completely unrecognizable products out of the oven.
The notes detail 5 specific mixing methods, and I want to look at them conceptually rather than just, reading down the list.
Good idea.
Let's start with the techniques designed to prevent structure. The text outlines the rubbing in method, where butter is rubbed directly into flour. It explicitly says this is used for shortbread, scones, and crumb toppings.
Right.
Why does rubbing the fat into the dry flour create a crumbly scone instead of, say, a fluffy cake?
Well, we have to look at how gluten forms.
Okay.
Gluten is the elastic protein network that gives baked goods their chew and their structure.
Right.
It only forms when the proteins in the flour, specifically gluten and gliadin, come into direct contact with water.
Ah, okay.
In the rubbing in method, you are taking solid fat and mechanically rubbing it until it coats the individual flour particles. You are effectively waterproofing the flour.
So when you eventually add a liquid, the water can't even reach the proteins.
Precisely. The fat acts as a physical barrier. Because the water can't hydrate the proteins, strong gluten strands simply cannot form.
Wow.
The dough remains tender, short, and highly prone to crumbling, which is the exact defining characteristic you want in a shortbread or a scone.
That's brilliant.
You are using physical friction to intentionally prevent a chemical bond.
Here's where it gets really interesting. Contrast that entirely with the kneading method.
Yes, the complete opposite.
The notes describe this as a push-and-fold technique specifically used to develop gluten in bread. Here, we aren't trying to prevent structure. We're trying to forcefully build it.
Right. Kneading is an application of aggressive kinetic energy.
Yeah.
With bread, you want a strong, resilient, chewy crumb that can trap massive amounts of yeast gas without tearing.
Right. Otherwise, it goes flat.
Exactly. By forcefully pushing and folding the hydrated dough, you are taking those randomly tangled flour proteins and manually stretching them out. You're forcing them to align into organized interlocking sheets.
Oh, wow.
You are literally weaving a microscopic elastic scaffold through brute force.
So rubbing in builds a waterproof wall to keep the dough weak, and kneading builds an elastic scaffold to make the dough strong.
That's a great way to summarize it.
But what about the other 3 methods in the text? the creaming method, the whisking method, and the folding method. Looking closely at the notes, all three of these methods share a unified obsession, which is managing air.
What stands out to you when you look at these three?
Well, it seems like they're all just different strategies for trapping bubbles.
Exactly. Aeration is the great secret of late, tender bakes. Let's examine how the text differentiates them.
Okay.
The creaming method involves beating solid butter and sugar together until light and fluffy, resulting in soft cakes and cookies. Mechanically, what do you think is happening between the sugar and the butter there?
Well, going back to what we learned about sugar being dense and crystalline,
Yeah.
I imagine those hard little sugar crystals are acting almost like tiny shovels or like bulldozers.
Oh, I like that.
As you beat them into the solid butter, the sugar crystals are physically carving out tiny microscopic pockets, right? And dragging air down into the fat with them.
That is an incredibly accurate way to visualize it. The sharp edges of the sugar crystals literally punch holes in the plastic fat, trapping millions of tiny air bubbles.
Wow.
When the cake hits the heat of the oven, the leaveners produce gas that expands those pre-existing bubbles, creating a soft, tender lift.
But the whisking method achieves lift in a totally different way.
It does.
The notes say this involves whisking eggs and sugar specifically to increase air, used primarily for sponge cakes. There's no solid fat here to punch holes into.
No, there isn't. Instead of carving into fat, the whisking method relies on unraveling protein.
Okay, unraveling protein.
As the whisk rapidly drags through the eggs, the mechanical shear force physically unfolds the tightly coiled egg protein.
Oh, okay.
And as they unfold, they link together around the air bubbles being driven into the bowl. So they create this flexible, watery protein net.
So creaming uses sugar to trap air inside a fat, while whisking uses shear force to trap air inside an egg protein net.
Precisely. And that delicate trapped gas leads directly to the final technique mentioned in the text, which is the folding method.
Right.
The notes describe this as gentle mixing to keep batter airy, heavily used in things like chiffon and muffins.
This one feels like a hostage negotiation.
It really does.
You spent all this time using the creaming or whisking method to trap millions of microscopic air bubbles. Now you have to add the heavy dry ingredients, the flour, without popping them.
Yes, it's very precarious.
If you take a chiffon batter and you aggressively knead it like bread dough or beat it with a whisk, you destroy the matrix. The bubbles pop, the gas escapes, and your cake comes out of the oven looking like a dense rubber disc.
You are dealing with an incredibly fragile foam.
Yeah.
Folding requires a specific sweeping under and over motion with a spatula.
Right. You're not stirring it.
No, definitely not stirring. The goal is to incorporate the mass of the flour into the batter with the absolute minimum amount of friction and shear force possible. You are essentially sacrificing efficiency to preserve the architecture of the air.
So what does this all mean for us? When we opened this deep dive, we talked about how a standard kitchen allows for intuition and, on-the-fly adjustments. But our source material today proved that the bakery is a rigorous, unforgiving laboratory. We saw the domino effect of inaccuracy, right? How an overpacked cup of flour creates a moisture vacuum.
Yes.
And how the dense geometry of sugar can literally burn your house down if you don't weigh it on a scale.
We also observed how the very identity of an ingredient shifts based on temperature.
Right, the butter.
Transforming solid butter from a structural fat into a fluid hydrating agent the moment it melts.
And most importantly, we learned that the exact math is totally useless without the exact physics.
Right.
The kinetic energy we apply, whether it's rubbing fat into flour to prevent gluten for a scone, aggressively kneading dough to build a scaffold for bread, or gently folding a chiffon batter to protect a delicate matrix of air.
Yes.
That physical movement is what truly dictates the final texture of the food.
It reveals a rather profound final implication about the nature of this science, I think.
Oh, yeah?
We have established that the metric scale prevents a cake from collapsing or burning, but it is the physical method, the pushing, the whisking, the folding, that actually decides whether those identical ingredients become a dense cookie or an airy sponge.
The action determines the identity.
Exactly, which suggests that even in a discipline ruled by rigid chemistry and exact digital weights, the baker's own physical movements,
Wow.
the specific velocity of their whisk, the deliberate pressure of their hands, the gentle arc of their fold,
Yeah.
that energy is actually the final invisible ingredient in every single recipe.
You can standardize the measurements, but you can never remove the human kinetic energy from the equation. That is a brilliant place to leave it. Thank you for joining us on this exploration of measurements, methods, and the absolute chaos of a tablespoon of baking soda. I'll see you next time.